Welcome to the First Mold Insights, where we talk about injection molding, rapid tooling, product development, and real world manufacturing insights. Today's topic is the injection molding cycle. Alex, we talk a lot about injection molding in general, but the cycle itself is where the rubber meets the road. Before we even get to the melt being injected, there's a whole series of critical prep steps. What's one of the most common oversights you see product teams make right at the start that can really mess up a cycle?
You know, Mia, it's often something as simple as material inspection. People think, it's in the bag, it must be right. But we've seen orders where the wrong material type or color was delivered. Or, more subtly, the packaging is damaged and the material's contaminated, especially for transparent parts. That immediately throws your whole cycle and your part quality out the window.
Huh, interesting. So it's not just about getting the right resin, but ensuring its integrity before it even touches the machine. What about coloring? Many products aren't natural plastic color. How does that fit into the preparation?
Right. Most plastics come in natural, white, or transparent. If you need a specific color, you're adding color master batch or powder. The key here is consistency. We adjust the ratio during trial production, get those color limit samples approved, and then in mass production, you follow that material requirement sheet to the letter. And crucially, always clean your mixer thoroughly, especially if you're switching colors. Kerosene or mold cleaner for colored materials.
Okay, so material readiness is huge. And then there's drying. Why is that such a critical step before molding?
Oh, drying is absolutely non-negotiable for many materials. If you've got excess moisture, you're going to see splay marks, bubbles, sink marks on your product surface. Worst case, it can degrade the plastic itself, impacting strength and appearance. Think about ABS, PA/PC, PMMA. Those are highly moisture absorbent. PE, PP, PS, PVC, POM. Less so, but still. You've got to be aware. Drying effectiveness really boils down to temperature, time, and the material's thickness.
So, if you dry a batch of ABS, but it sits for a while, you'd need to re-dry it?
Exactly. Materials can reabsorb moisture. If it's not used quickly, you'll need to dry it again under the same conditions. It's a common mistake to assume once dried, always dried.
Got it. And beyond the material itself, what about the equipment, the machine, the mold?
Yeah, equipment cleaning is another big one. If you're switching between different plastic types or colors, you can't have residual material from the previous run in your machine's barrel. That'll cause quality issues, easy breakage, lack of elasticity, color deviations, even black spots, or nozzle clogging. So when we switch molds, we do a thorough machine clean.
Makes sense, and then the mold itself. Cleaning it, connecting it up. What's involved there?
Well, first, mold cleaning. You've got to get all the rust preventative oil off the surface, cavities, gaps around inserts, runners. You don't want that sticking to the product or clogging up vents. For mirror finished products or anything with strict appearance requirements, you can't use cotton swabs or old rags that'll scratch the surface. We usually rinse with mold cleaner and blow dry with an air gun. And it's best to clean the mold before mounting it on the machine. It's just easier and saves time.
And then the connections? Water, hot runners.
Right? For part appearance and productivity, you need to connect the mold to water, the mold temperature controllers, and chillers. You want a stable temperature minimally influenced by outside factors. It usually takes 15 to 30 minutes to get to the right temp after connecting the water. If you're using a hot runner mold, you also connect that power supply after mounting and preheat it for another 15 to 30 minutes until the control box shows it's at the set value. Only then do you begin trial injection molding.
Okay, so that's a lot of prep just to get ready. Once everything's prepped, Alex, walk us through the actual steps of the injection molding cycle itself. Where do we begin?
So, the first step is clamping. This is where the machine secures and holds the mold closed. It applies a specific clamping force to counteract the high pressure of the molten plastic during injection. You often hear about machines being 1,000 tons or 500 tons. That's the maximum clamping force they can exert. The clamping unit itself has fixed and movable platens, tie bars, and a mechanism, either toggle or hydraulic, to deliver that force and seal the mold.
So it's about holding everything together against immense pressure. What's next?
After clamping, it's injection. The material has already undergone plasticization or melting. Now, the machine's screw or plunger moves forward, pushing that molten plastic through the nozzle and into the mold cavity. It's really about precise control of injection speed, pressure, and timing. You're filling that cavity, making sure the molten plastic takes on the exact form and dimensions of the mold. We often call this the filling process.
And once it's filled, what happens while the plastic solidifies?
That's the dwelling or cooling step. The mold stays closed, maintaining pressure on the solidifying plastic. This helps prevent any shrinkage or warping. The cooling time varies a lot based on the material, the part geometry, and other factors. Proper cooling is absolutely crucial for part quality, ensuring uniformity and strength. We might use cooling channels in the mold or external methods like air or water cooling.
So once it's solid enough, the mold opens. What's the process there?
That's mold opening. The clamping unit releases its force and the movable platen retracts from the fixed platen. This creates a gap between the mold halves, allowing the molded part to be removed. It's usually a slow, fast, slow movement to ensure smooth separation.
And then getting the part out?
That's ejection. This is where the ejector system pins or plates within the mold actuates to push the part out of the cavity. Increasingly, especially in China, we see automatic robots handling this, capturing the molded parts. Ejection has to be carefully controlled. Too much force or the wrong speed, and you can damage or deform the part. We also use things like air blasts, stripper plates, or those robotic systems for complex or delicate parts.
Right, so you've got your part out. And then the final step before the next cycle?
It's mold closing. The clamping unit brings the mold halves back together, aligning them and setting up for the next cycle. And then we're back to clamping again.
Alex, that whole sequence, from clamping to mold closing, defines the cycle time. Why is accurately estimating and then optimizing that cycle time so important for a manufacturing operation?
Maya, it's everything, especially for high-volume projects. For low annual production, an underestimate might not hurt too much. But if you're making millions of parts a year, even a second off, your estimate per cycle can mean huge losses or gains. We've seen it. It's why in a profitable factory, the mantra might well be cycle, time, flow. Analysis helps, but it can't predict every variable: mold conditions, machine quirks, or even operator performance. So, accurate estimation is crucial when quoting for injection molding parts.
Okay, so it's directly tied to profitability. What are the main components that make up that total cycle time? I imagine it's not just the cooling phase.
Oh no, it's 11 distinct steps that combine for the total cycle time. You've got mold closing and locking time, then filling time, packing and holding time, screw delay time, screw plasticizing time, Screw retract time after rotation. Cooling time, cooling delay or idle time before mold opening time, part ejection, and finally, ejection mechanism return time. To reduce the overall cycle, you have to look at optimizing each of those individually and how they interact.
That's a lot of moving parts. So, for a factory trying to boost profits or a product team wanting to get to market faster, how do you actually reduce that cycle time without compromising quality? What are some key techniques?
Well, first, mold design optimization. A well-designed mold is fundamental. Think proper gate placement, optimized runner design, efficient cooling channels. Mold flow analysis software helps us identify improvements there. Then T here is clamping and opening time optimization. New machines feature regenerative clamping hydraulics. For example, that can speed up those 4 stages of clamping and 3 phases of opening.
And for the actual injection itself?
Injection time optimization. You can use high injection speeds during the filling phase as long as you're not causing defects like bubbles or burning. Then, for holding time, that starts after injection, usually at a lower pressure. Its main job is to compensate for shrinkage, making sure the part is full and doesn't have dents. Once the runner solidifies, holding pressure isn't doing anything, so you can end it there. We'll often weigh the product or check for dents to find that sweet spot.
So, you're looking for the minimum effective holding time. What about cooling? That's usually the longest part, right?
Often, yes. Cooling time optimization is huge. This is the period from the end of holding pressure to the start of mold opening. The goal is for the product to be cool enough not to deform upon ejection. You start with a longer time and gradually reduce it until the product just stops deforming upon ejection. No need to go shorter after that.
And charging time? That's when the screw is preparing the next shot, right?
Exactly. Charging time optimization. If your charging time is longer than your cooling time, you've got insufficient plasticizing capacity, and that's going to bottleneck your cycle. You can enhance plasticizing capacity by using barrier screws, larger diameter screws, or increasing screw channel depth. You can also increase screw speed, but be careful with shear-sensitive plastics like PVC or PET. That's a definite no-go. Reducing back pressure helps too. Or using hydraulic shutoff nozzles, which let you plasticize during clamping and opening.
That's clever. Plasticizing while other things are happening. Any other temperature-related optimizations?
Yep. Barrel temperature optimization. Using the lowest barrel temperature that still ensures smooth injection filling can actually shorten your cooling time. Also, clamping force optimization. Use the lowest possible clamping force that doesn't produce flash. This shortens the high-pressure locking time and extends the life of your mold and machine.
And cooling efficiency? Are there ways to get more out of your cooling system?
Absolutely. Cooling efficiency optimization through better mold water channel design, improved heat exchange, and uniformity mean shorter cooling times. You can even use ice water cooling if your product quality requirements allow for it. Finally, ejection time optimization. On small injection molding machines, a pneumatic ejection can be faster than hydraulic. And with independent hydraulic, pneumatic, or electrical controls, you can even achieve simultaneous mold opening and ejection. For multiple ejections, using the machine's vibration ejection can save time because the pins don't have to fully retract each time.
Wow, so many variables to fine-tune. Alex, given all these techniques, what's the single most important thing for product teams and manufacturers to remember when they're looking to speed things up?
Look, The biggest takeaway is this: you can chase speed, but never, ever at the expense of part quality, dimensions, appearance, functionality, or material integrity. That's a false economy every time.
Thanks for tuning in. For more manufacturing resources or custom part production services, visit firstmold.com. We'll see you next time.